Okay, good morning. We have a couple of administrative things to take care of. I was told many years ago that people who write slanted, I can never tell when I'm right here how slanted that is, but it's pretty slanted, right? I've heard that people that write slanted up like that are happy people.
What if it's straight?
Straight, you're miserable. I don't know. I've heard it. It's not true. I mean, I'm not happy. So anyway, okay. So our exam for this is like the 10th time I think I've said this, is going to be Monday, not on Wednesday. The schedule says Wednesday, but it's on Monday. The review I sent email, I think I printed out like 25 copies or so. So I'll pass this out today just in case you didn't print it. We're not going to have a whole lot of time to go through the review problem by problem. So I will be posting the solutions to this review later today. All right. Well, maybe tomorrow. All right. I've started working on it. I got through the first 4, but I just need to finish up the rest. And then in the email I sent to you with the review, I said we still haven't covered some of this stuff, and that's what we're doing today. All right. So I'm going to get right down to business. Yes? Okay. So we were talking about logarithmic functions last time, and the main takeaway was that a logarithmic function is just the inverse of an exponential function, and that if you go to graph them, all you're going to do is switch the x and y's of the exponential function. That's what I asked you to do for homework, those three problems. Now what we're going to do is we're going to talk about the properties of logarithmic functions and exponential functions. So this is where things start to get kind of weird, all right? Properties of logs. So you're going to hear me say logs from now on, and when I say logs, I'm talking about logarithmic functions. All right, so let's look at some of the properties of logs. First of all, if you take log of any base of 1, what will our answer be? So let me see, I still have my sticks from last time. We got to move kind of quick here today, so I may not have a whole lot of time for this. Let's see, Macy, is Macy here? Macy, I called you last time, so it's this stack. Andrea? Okay, how you doing, Andrea? Good morning. Okay, so do you remember from last class what question this is actually asking you? You weren't here? Okay, yeah, and I haven't put the video up. Okay, so let's move on. Zeke? Were you here?
Yeah.
Do you remember the question this is asking?
It's a raised to what power is 1?
Exactly. A raised to what power is 1? So a raised to what power is 1? 0. Okay, so notice that this is a property, okay, which means this holds for any log. If you have any log and you have any base, remember that base has to be a positive number, can't be 1. So if this is log base 3, log base 10, no matter what the base is, if you have 1 here, the answer is always 0. Because no matter what the number is, raise it to the 0, you get 1, right? So that will hold for all logs. Another way of saying this is if you plug 1 into a log function, you're going to get 0. So on your calculators, you can try this yourself. Remember, your calculator had 2 keys. Remember, it only had 2? So if you try log 1 or natural log of 1 on your calculator, it should spit back 0. All right? Okay, that's the first property. Second property, log base A of A equals. All right. Kristen, I don't think I called you last time, did I? So what is the question that this is asking?
So it's asking a raised to what power
Is itself. So a raised to what power would be a? What do you think, Kristen?
So
1, right? 1. Okay, so this is going to turn out to be an extremely important property right here. All right, this one. So does it all make sense to you? A raised to the first power is a. Remember that little loop I was talking about last class? The loop works, right? A raised to what power gives you a? Well, 1. A raised to the 0 gives you 1, right? Okay, next property. Oh, by the way, over here. Man, I'm not used to not having a towel. Okay, so this was an example of that first property for the log and the natural log, right? The two special ones. How about over here? If I were going to look at this property for the special logs, then this is telling me that log of 10 would be 1. Let's see, does that make sense to you? Because remember with this log, I told you that we don't write the base down here. It's understood that the base is what? 10, right? So there's really a 10 down here. So log base 10 of 10 is 1. Again, you could go to your calculator and type that in. What's log of 10? And you should get 1 out. Yes? Okay. So what would it be for the other special log? ln, what would have to be here to get 1? What's that? E. Okay? Look, because what's the base? It's not written here. What's the base of this log? E, right? It's a special log. So if we plug E in here, we should get 1. I'm going to box this. I'm going to box it again. I'm going to put a star next to it. The natural log of E is 1. Okay? The natural log of E is 1. Okay, let's go to the third property. The third property says that log of any base, A, of A raised to any power n should be equal to, so let's think about what this is saying. A raised to what power is A raised to the n power? A raised to what power would give you A raised to the n power? What do y'all think? N. Does the loop work? Does the little loop work here? A raised to the n, does that equal A raised to the n? It does work, right? A raised to the n is equal to A raised to the n. Now, of all the properties that I put on the board, of these 3 properties that are up here, the most important one is the 3. All right? This is the most important one. We're going to use this a little bit here, okay? So let me show you this property with a couple of examples. What would log base 4 of 4 cubed be? 3. Right? What would log base 7 of 7 to the negative 2 be? Negative 2. Right? All this does, the way you want to look at this is that if you look at a to the n by itself, would you all agree that a to the n power is an exponential function? Exponential? And what we're doing is we're taking that exponential function and we're applying a log to it. And what do exponentials and logs do to each other? Remember, what was the whole idea behind the log? It was the inverse of the exponential, right? So what happens is first you do a to the n, which is exponential, but then you undo it with the log. So what happens is this power just falls out. That's the big picture of what you need to take away from this. When you put the exponential together with the log, you get the power to fall out. Okay? You put the exponential 4 to the 3 together with the log base 4, the 3 falls out. You take 7 to the negative 2, which is exponential, apply the log, the negative 2 falls out. Understand? So now let me do a couple more examples. How about this? What would log of 10 cubed be? 3. The reason it's 3 is because when I write log, what's the base down here? 10. So this looks like log base 10 of 10 to the third. So this should just be 3. Okay, this one. What's natural log of e to the 5? 5. Again, because the natural log is really base e, and so you have really log base e of e to the 5 falls out. Do y'all see what I'm saying? This is where things start to get weird. I mean, you have to really kind of keep track of what's going on here. Any questions? Why are y'all looking at me like that? I didn't make this up, okay? I'm just here to deliver the message, yes? Y'all look mad at me. Okay, moving on. Let's see, any other properties we want to put up here? All right, let's go to the fourth one. This one's not as useful, but it will be used sometimes. If you have log of any base, and then inside you have two things being multiplied. Then you can rewrite this as 2 logs being added. Okay, this property is strange. It is not distribution. Okay, you know how if I give you this expression 2 and then I put x plus 3 here, you could distribute the 2 through the parentheses, yes? That's not what's happening here. We're not distributing a log through. This is just a property. Anytime you have a product, multiplication, inside of a log, you are allowed to split it into 2 logs with addition between them. And this is just a property, you're just going to have to take it on faith, and we move forward, all right? So let me give you an example of this. Okay, give you an example. What would this be? Log base 4 of 4 x squared. Let's just do 4 times x. Use this property right here. So do we have log base of something, and then do we have multiplication inside? 4 times x, right? So what can this be turned into? Log base 4 of what? 4, and then plus log base 4 of x. Okay, now looking at those two, that first log base 4 of 4, that's a property. Which property is that? I've given you 4 properties now. What property can I use on that first log? Property 2. This looks like log base a of a, right? That's really asking you 4 to what power gives you 4. So what's this whole thing turn into? 1. This is 1 plus log base 4 of x. Now I can't do anything to this, because x is a variable, I don't know what it is, right? Doesn't have a 4 in it, so I can't use any of the properties. All right, 5th property. If you have log of any base, and this time instead of multiplication inside, you have division. So instead of 2 things being multiplied, you have division. Any ideas of what that might turn into? If we had multiplication inside of 1 log, it turned into 2 logs with addition. Have a hunch as to what would happen here? 2 logs with subtraction. Okay, what's going to happen here is you're going to get a log base a, and you're going to start with the numerator x, and then subtract from that log base a of y. So this is a property. Again, you just have to take it on faith, and we move on. Okay, last one. Log base a, oh, I lied, there's one more, sorry. X to the n. Okay, I want you to look at property 6 and compare it to property 3. Are they the same property? No, what's different? This thing here is x, not necessarily a. This property works if the base and the base here are matching. Then they kill each other off because they're inverses, and then you just drop the n out. Here, this a and this x aren't necessarily the same. so they aren't necessarily inverses, so they don't kill each other off. However, there is something you can do with this, and that is, you see this power here? You can drop it out to the front. Watch, n log base a of x. That's what that is, and that's multiplication in the front. So this property says that if you ever have a log of anything, like log of any base, and you have something raised to a power, and that something doesn't have to match this. If anything raised to a power, you are allowed to just take that power and drop it out front. You're free to do that, all right? I won't get into the technicalities of why, but it actually is just using this property right here, but we won't get into it, all right? I'm going to put a star next to this one. This one's very important also, all right? I'd like to show you property 6 with a few examples. So using property 6, what would natural log of 2 to the negative 1, how could I rewrite that using property 6? Yeah, this is a log, right? Okay, so here's a log. Do we have something to a power? 2 to a power, right? What can I do with the power then? Yes? Yep, negative 1. Negative 1 times natural log of 2. That's it. That's that property in action. Let's do another one. What's natural log of 4 to the 3x? How could I rewrite that? 3x times natural log 4. That's it. I just want you to see the property and how it's used. Doesn't matter what the log is. If you have something to a power, the power can drop out. All right? One more. That's a t. Log of 3 raised to the 0.15 t. I can rewrite that how? 0.15 t times log 3. All right? Okay. All of these properties are for a reason. All right? We're ready to do something now. Before I actually do this, I should say something. In this class, we have graphed lines, haven't we? We've graphed parabolas. We've graphed polynomial functions. We've graphed rational functions. We've graphed exponential functions. And last time we did log functions. We are done graphing functions, all right? So now what we're going to do is tackle something new. We want to talk about solving equations. And right now, as a student in this class, there are certain equations you should be comfortable solving. One, okay, so let's recap what we can do. When it comes to solving equations, everyone in here should be okay with linear equations. Okay, we'll just call that one, linear equations. An example of this, 3x minus 4 equals 2 parentheses x minus 1 plus 7. If I asked you to solve that equation, that's like one of the problems from the first day of class. You look at this, you say it's linear, you try and get all your x's on one side, all your numbers on the other, right? But we have a method of doing it. We've done it. Maybe that would be difficult for you right now, but it's in the past. We've done it, yes? Okay, so we can say check on linear equations. We can handle those. Okay, what is the other type of equation that we've looked at and we've actually spent some time trying to be able to solve? Quadratic equations. Okay, so it comes to a quadratic. When it comes to quadratic equations, something like 3x squared minus 4 equals 5x. What we do with quadratics is we move everything to one side, right? Make it equal 0, and then we look, is it a special case? Is it missing the x term? Is it missing the constant? But at the end of the day, we always had what? If everything else failed, what did we have for quadratics? Quadratic formula, right? So we can handle quadratics. We don't have an issue with that. Now, today, and all this stuff with logs, is to lead us to a new type of equation, all right? Our goal today is to solve what are called exponential equations and log equations. Those are two different things. Okay, we want to be able to solve exponential and log equations. Those are two separate types of equations, all right? So let me try and motivate this idea with an example. Very simple example. Alex? Where's Alex? No Alex? Evan? I feel like I called you last time. No? Evan? Okay, this is an equation, right, Evan? Everyone agree that's an equation? You have an equal sign? Okay, you have a variable x, yes? Where's that x, Evan? I mean, where is it? Is it like this? Is it like an equation like this? So Evan, what's the difference between the x here and the x there? Look at its position in the equation. Okay, so x over there is up in the exponent, right? And x here is down in the base. This is a quadratic equation, right? Because x is down in the base, down on the bottom, and it's just being squared, which made it quadratic. There, the x is up in the exponent. Totally different thing, yes? So the question becomes, how do we solve for that? How do we get an answer, x equals something, right? Now, if we look at that, we might be able to get the answer just by looking, right? Because that's really saying, Evan, 4 to what power is 16, right? That's what that's saying? Everyone agree? 4 to what power is 16? So what is that? That would be 2, right? The answer is 2 just by looking. But the main thing about that example is that I want you to see the difference between what we've done in the past and this equation. Okay, let's try a different one. Okay, exponential equation. That's an exponential equation because the variable is up in the exponent, right? Can you look at that and give me an answer? You cannot. You cannot, all right? You cannot do that. Because that's saying what is this really saying? It's saying 4 to what power is 12, right? Wait a minute, 4 to what power is 12? Haven't we said that before? We said that all last class. We've started saying it this morning. Isn't that what we were doing with logs? Is that not the same question we were asking with logs? So maybe I can rewrite this using a log instead. So let's see if we can reformulate this with a log. Log, what would I put down here for the base? 4, right? And then what here? 12 equals, oh shit, no? Isn't this right here, this equation, equivalent to that question? 4 to what power is 12? Isn't this the same thing, right? This is the same thing. You can double check to make sure that it works by just doing the loop. If you do this loop, 4 raised to the x is 12, right? Equals 12. That log is that equation. Agreed? Let's try now. So the answer is this. X is, what I'm trying to get at is in this equation, the x was up on top, right? Stuck up in the exponent. Now in this equation, is x up in the exponent anymore? No, right? X is just sitting here. X equals this. Now what is this? I don't know, right? We still don't know. What is 4? 4 to what power is 12? We still don't have that answer. But I want you to see that this exponential equation got turned into a log equation. Yes? Okay, I'm going to leave this as an open question. We still don't know what this is, all right? But let's practice doing another one. We'll be able to solve it. Just hang tight. Okay, what about this? 3 to the x plus 2 minus 4 equals 17. Frank, what type of equation is this, Frank? Almost, not yet. Exponential. The reason being, the variable we're solving for is up in the exponent, okay? So maybe we can do the same sort of process we did here and convert it from that to a log. So this is saying 3 raised to some number plus 2 minus 4 equals 70. This is somewhat complicated, isn't it? Do you all agree that's definitely a lot harder than that? You can look at that and get an answer here. I don't think anyone's going to give me an answer here. But let's work through some steps. First, what is this step? So what do I do there? What did I do? I just added 4 to both sides of the equation. I can do that, right? I'm allowed to do that. Now, when you look at this, isn't this really saying like 3 to this power is 21, right? 3 to something is 21. 3 to something is 21. Let's now try and write this using a log and a loop. So Frank, go ahead. Log, what's the base of the log? 3, okay? And maybe, Frank, it's easier to write the equals here and come up with the loop this way. So you want to do this? Yeah. What's this going to be? X plus 2. And then what goes in here? 21. Okay? 3 raised to the x plus 2 is 21. That's that equation, right? 3. But notice now the x is no longer up in an exponent. We have a method here using logs that allows us to take that variable that's trapped up at the top and somehow bring it down. Now we still don't know what this is, right? We still don't know what that is. I'm going to give you a formula in a second and we'll be able to get that real easy. All right? Let's practice one more. Okay, how about this one? 2e to the 3x minus, plus 1 minus 7 equals 11. Who's the lucky one here? It's L. Okay. Exponential equation. Where's the variable? Up in the exponent, right? So this is exponential equation. When we have exponential equations, what we're going to try and do is turn them into logs, right? Okay, before we can try and do the loop, like on this one, we went right to the loop, didn't we? Okay, this one we have to do a little bit of work first. Move that 4 over. So any ideas of what we should do before we try the loop here? Add 7 to both sides. Everyone good with that? Okay. 2e to the 3x plus 1 equals 18 when I add 7 to both sides. Okay, what's your gut telling you here? Should I do the loop now or should I not? I'll do a drum roll here. What about the 2 out front? You see that 2? It's multiplied, right? So this 2 is really a multiplication right there. What can I do to get rid of that 2? Divide. Okay, do you all agree I can divide both sides by 2 right now? Okay. What I'm trying to do, or what we are trying to do, is truly get something to a power equals a number, and just nothing else, right? No other, we don't want this -7 here, we don't want this 2 out here, we just want this thing right here by itself. So that's what we're shooting for. Okay, so my next line should just be, because the 2's cancel, right? So we get e to the 3x plus 1 equals 9, right? And now you can do the loop. Stephanie, What's the base of the log that I'm going to use here? Nope. What was the base of the log we used here? 3, right? And where did that 3 come from in here? It's the base of this, right? So what's the base of this expression here? What's the base we have? No. This is 3 to this power. This one is this e, right? Log base e. Okay, and then I'm going to put the equals here, and let's just think about this loop. We're trying to basically rewrite this using this idea. So what goes over here? 3x plus 1. And then in here, 9. What do y'all think? Again, we have found a way to take an equation. Did you just clap?
Oh, no.
No, hell no, you're not clapping for this. I know, I'm giving you a hard time. Okay. So we have x up here, right? And we've somehow done all this stuff, and now x is sitting here. If we could just get x by itself, we'd be done. We still don't know how to handle this, right? We didn't know how to handle that. So I've left us hanging on all these problems. How are we going to figure out what this is? So this answer back here requires us to use the log base 3, right? Our calculators only have, well, most of them only have 2 keys. Which ones are they? The log, which is base what? The log is base what? 10. And then the other one, ln, is base e, right? Base e. So I cannot use my calculator for this, right? Could I use my calculator for this? This is log base e, isn't it? So I could use my calculator for this because this is actually the natural log of 9. That's what that really means. Okay, but I'm still going to stop here because I need to give you the final property of the day, which is, it's actually a formula more than it is a property. This is called the change of base formula. Okay, and here's what it is. It says, let's say you have a log, let's say you have a base, and then let's say you have some number here. I'm going to call it little b. Okay, that's what we have here, right? Log base a of b. Log base a of b. Got it? So here b is 21, and here a is 3. Here b is 9, a is e. This formula says that this is equal to the natural log of b divided by the natural log of a. This is extremely useful. I'll give 5-point bonus on the next test for somebody who can summarize how important this property is. Pardon? Very important. Good job. No. I mean, like why is this so important? What is this property, this formula, allowing us to do? What's that?
Solve it with the
Solve a little more. She's saying solve it. She said solve it with a calculator. Solve
log equations
that aren't base 10 or e. Is that what you're saying? With a cal. This allows you to calculate the value of any log you want, using natural logs, which your calculator has. So exactly what you said. This allows you to solve any log with a calculator. All right? That's why your calculator only has, technically your calculator only needs 1 log key. It only needs 1. But it gives you both the log and the natural log. This formula is going to be very, very handy now. All right? So let's go back over, let's see, did we have an example before this one? We did, didn't we? We were, and I stopped. Let's go back to that one. What was it? I'm going to put it over here. At the very end, what did we have? Log base what? 4, and then 12, and then equals x, right? Weren't we there? That's where we were? Okay, let's revisit this. This side is log base a of b. Yes? Log base a of b. So according to the change of base formula, this can be rewritten. The left side of the equation can be rewritten as natural log of 12 divided by natural log of 4. And there we get our calculators out. So everyone needs to make sure that you can do this on your calculator correctly, because there are many ways to type this in wrong. So I'm going to tell you what the answer is here. I'm getting so this should be equal to x. I'm getting 1.7924 something, right? So 1.79 equals x, and I'm going to box the answer. I'm going to put the change of base formula over here. Okay, so let me recap. Let me recap this problem right here, okay, because it's not on the board, but I want to recap it. This problem, when I started it, said 4 to the x was 12, right? That's what it started as. And we said, okay, 4 to some power is 12. We've said that before. We converted this to a log. Using the loop idea, 4 to the x is 12, we got that. And then we rewrote the left side as natural log 12 over natural log 4 using the change of base formula. We figure that out in our calculator, we get 1.79 equals x. So, weren't we trying to solve for x? We have solved for x. So now to check our answer, what we could do on our calculator is do this. On your calculator, do 4, raise it to the 1.79. Okay, you're raising, we've done raising on these before, so 4 raised to the 1.79, I'm getting 11.958. Not quite 12. Why is it not quite 12? I rounded this answer. Okay, so that's okay. That's okay. We've got to round somewhere. So I'm just going to ask you right now, just round maybe 2 decimal places. See, so we found the answer, right? 4 to what power is 12? 1.79. Okay, let's go back to this one right here. We said e raised to 3x plus 1 is equal to 9. I thought there was more to that one. Was that the one? I thought the 9 came from something else.
It was 2e to 3x plus 1 equals 11.
Oh, okay. So, okay, I'm sorry. This was the second one then. Sorry, this was the second one. I thought that was the second one. This is the second one. Let's look at the second one. This is the equation we started with, which was a little bit different than this one, because we had some other junk over here, right? This 4, so we brought the 4 over, we got this. And we said, oh, okay, let's use a log, let's rewrite it, let's use the loop, we got to this. And we were at this point, we were stuck. But now, look at this side. I can figure this out on my calculator, right? So let's figure this out. What is it? Natural log of what? 21 over natural log of 3 equals x plus 2. So we have to use our calculator now. I'm going to erase this. I'll erase this one too. So we have natural log of 21, natural log of 3. So I'm getting on the left side there 2.771. I'll go 3 decimal places. I'm going to be crazy today. Go 3 instead of 2. All right, so there's my left side. Are we done? No, we haven't solved for x. We almost have x. To get x by itself right now, what do we need to do? Subtract 2 on both sides. So subtract 2 here, and when you do that, you get your final answer, 0.771 equals x. And that is it. So what this is saying is that if I replace that x with 0.771, then add 2, raise 3 to that power, subtract 4, I will get the number 17. All right? All right. So the main idea behind an exponential equation is you want to try and get the thing that has the exponential, the base and the variable, you want to get it by itself. Once you get it by itself, you convert it with a log. Once you get there, you use your calculator, change of base formula, you're good. Understand? Okay, that's exponential equations. Let's look at a log equation. Log equations are different than exponential equations. So for a log equation, an exponential equation, the variable's in the exponent, right? Where do you think the variable is in a log equation? Not in the base, in the log itself. So look like, I'll write one out here. Example. Log base 5 of x equals 3. So you could actually tell me what that answer is. I think you might be able to just tell me what that answer is. What is x here? If you understand how logs and loops work. 125. X is 125. Why? Because this is really saying 5 to the third is x, right? 5 to the third is x. So, but do you see that the x is in the log? It's not up in an exponent? So to do this problem, what we're going to do is instead of like this, where we went from an exponential to log, we're going to go log back to exponential. So I'm just going to take this and rewrite the loop. Like that. Right? That's what that says. 5 to the third is x. And 5 to the third power is 125. 5 times 5. Be careful here. The biggest mistake I see here, what do you think the biggest incorrect answer I get for that problem is? 15. Because what do students do? 5 times 3 is x. It's not 5 times 3. It's 5 raised to the third power. Let's try another one. Is that pretty straightforward with that loop idea? Okay, let's do another one. Okay, log base 2 of x plus 4 equals 5. Okay, is this an exponential equation? No. Is it a log equation? Yes, I mean, it's got a log. The x is in the log, yes? So anytime we see a log equation, we want to just go and try and do the loop. But you want to have the log by itself, right? Here we had a log by itself on this side of the equation. So we went right to the loop. Do we have a log by itself right here? I mean, it's log. This is all in parentheses, right? So that is within this log. So it is safe at this point to go to the loop. Do not distribute. You cannot. This is not a number, okay? Log base 2 is not a number. It's a function. So we're just going to go straight to the loop here and use that loop to rewrite it. So what should my next line be? 2 times 5? Raised to the 5 equals x plus 4. Now look at your x is right there ready for you, right? Ready to be solved for. 2 to the 5th power, 2 times 2 times 2 times 2, 32. Okay, so this is 32 equals x plus 4. Last step, subtract 4 on both sides. 28. X is 28. Okay. Let me pass out the review. Here, just take half this stack. Just take one kind of, let's get those out that way. Same thing here, just kind of. I need to give you another example here. Let me give you 2 more examples before we look at that. Everybody have a copy? We're not looking at that yet, but all right, take a look at this. You see the variable? We're good? Just keep it. You can give them to your friends if you want to take a couple of extra copies. Where's the variable? In the log, right? This is a log equation. Our goal then is to somehow use the loop to get it over to an exponential equation, which basically releases the x from the log. So, can I start thinking loop yet? No. Why not? That plus 4. So how do I get rid of that? Subtract 4 on both sides. Okay. So I think I've got the log by itself now, right? So now I can use the loop. So what's the base, Frank? The base, when log is written without any numbers down there, it's 10. Okay, so that, remember, that's one of the special ones. So we have to understand, we have to remember that because log wasn't, the base was not explicitly written for us, it is 10. And now we do the loop. See how that can be tricky? Because if you don't remember that, like, what are you going to use for the loop? So what is this, 10 times 2? No. 10 raised to the 2, right? 10 squared. 10 squared is 100. And then, we're doing this loop, like that. So now we go, and that's 100 equals x minus 1. So what is x? 101, 101. One more. I want us to do the same problem, but I'm going to change log. Anyone have an idea of what I'm going to change it to now? ln, natural log. Okay, so if that was the equation, we'd have the same first step. We'd still want to subtract 4 on both sides, wouldn't we? So we go natural log of x minus 1 equals 2, subtracting 4 on both sides. And now we try the loop. But what's the base? It's e, right? Because it's not written. So we have to understand this is really like an e down here and a log. Do you all remember I told you why last class we do these special notations? That it's historically because of using typewriters. I wish we would have never done that, because then we wouldn't have the special notations and the base would always be there and the students would always see the base and you'd always know what you're doing. But in this case, you have to remember that that's an e down there. So this becomes e squared equals x minus 1. And e squared, you get on your calculator, right? Do e squared. You have that key on your calculator. So e squared. So I'm getting from here 7.389 or something like that. I'll go 3 decimal places again. Equals x minus 1. Add 1 to both sides. And we're done. What do you think? Exponential equations, the variable's up in the exponent. We do it, we isolate the exponent, and then we convert it to a log. Log equations, the variable's in the log. We isolate the log, we do the loop, and then we solve the equation, right? When we're doing exponential equations, we're going to most likely need this formula. Otherwise, it's just knowing how the whole loop thing works. Not bad? Okay. So now, move on to the last concept. I only have 20 minutes. I don't think we're going to be able to get this in on the test, but let's see. It's on the review, but I may just make it a bonus problem. Simple interest. All right. I like to talk about this a little bit because this is actually like related to the real world. Is that a question, Frank? No? Okay. All right, so let's just talk about money for a second. Let's talk about banks. Not sure why a bank looks like a house, but there's a bank, right? So you have people over here, and these people need money. Why do they need money? They want to go buy a car, they want to go buy a house, they want to go buy that TV, they want to go get some new clothes, right? So they go ask the bank for money. If you want to buy a house, you have to get a loan, right? A loan. If you want to buy a car, you have to get a loan. If you want to go and get a credit card, right? Credit card is okay, they'll give you money, but you have to pay it back, right? With what? With interest. So if you borrow money, okay, so these people, the ones that borrow, they go to the bank, they go, give us money. The bank says, okay, we're going to give you money. You got to pay it back, but you got to pay it with interest. So let's say you borrow $1,000. You're going to wind up paying back how much? Well, it'll depend on the interest, right? How much interest they charge you. How many of you have credit cards? You don't have to answer this, okay, if it makes you uncomfortable. No? Okay, if you have a credit card, do you know what your interest rate is? Most credit card interest rates are above 15%. Some are even 20-something percent, 26%. What does that mean? We're going to talk about what it means here in a second, but it means you're going to pay back about 25%, roughly. So if you borrow $1,000, how much will you wind up paying back? 1,000 plus 25%. What's 25% of 1,000? About $250. So they go, okay, look, I'm going to lend you 1,000. You're going to pay me back 1,250. The bank just made money, right? Now it takes them time to make money because you got to pay it back over time, right? But the longer it takes you to pay, the more that interest accumulates. So they're making money off of you, right? Where do they get the money? Oh, these people. These people have money, right? And where do they put their money when they get paid? In the bank, right? Okay, so they put that money in the bank. Now that money is not actually in the bank. Like if every person who had money in the bank went to the bank and said, give me our, we all want our money, like right now, everyone, the bank would not have the money, okay? Why not? Where's the money? Where's the money that these people have in their bank accounts? It's with these people, okay? So what the bank is doing is it's taking money here, saying, thank you very much. Thank you for putting $1,000 in here. We're going to pay you for giving us your money. How much are we going to pay you? 25%? Not even close, like 0.2%, like nothing basically. Okay, but a little bit. You get a couple of dollars every month for giving us your money, right? But we're going to charge you a fee anyway to use our bank. So basically they're getting this money for free, right? And they're turning around and they're handing to these people and then they're making money off of it. Does that make sense? Okay. So simple interest is a formula that we use, we as in bank, people, banks, to calculate how much you're going to owe if you borrow a certain amount of money after a certain amount of time. All right? So that's what I'm going to cover now, is the simple interest formula. So have you all ever seen at a bank this thing, FDIC, $100,000 or something like that? FDIC. So this basically means at a bank that if you have money in the bank and everybody went to go get their money and the bank's like, we don't have your money, the federal government will insure your money up to $100,000. So that means if the bank says, we don't have all these people's money, the federal government will come in and say, okay, how much did you have in there? 30,000? Fine, here's 30,000. Okay, and they'll do that, but they only insure it up to 100,000, which means you never want to have more than $100,000 in a single bank, right? Because then if things fall through, then there's your money. So you go to several banks, right? What's crazy about that is where's the federal government getting the money from? The taxpayers, right? Right? But we're in a deficit. The federal government is in a deficit, right? We owe money, don't we? We've gone and borrowed money from China. So China's like our bank. The US government has a bank, and its bank is it's crazy. Okay. All right, so simple interest. All right, here's the formula. Let me write it down first. There are two formulas. First one is this one. Just write it down. We'll talk about it. Okay, that's our first formula. And our second formula is this one. E, that's that special thing. Okay, those are our two formulas for simple interest. Let me explain what every single letter in these formulas means. Okay, P, let's start with capital P. Capital P in this formula is called the principal, but it's the starting amount. So let's say you go borrow, you go buy that TV you've always wanted on your credit card, and you go charge, $2,000. That's the starting amount. That's your P. Or if you go and put money into an account, like you're the people with the money, you go put it in, that's how much money you put into the bank. No matter what, that's your starting amount, all right? R is the interest rate. T is time, and it's always measured in years in this formula. Okay, it's time in years. What am I missing? N, okay, N is a weird one, so just write it down, I'll explain what it means in a second. N is the number of times the interest is compounded per year. Per year. That's YR there at the end. Per year. So when you put money into an account and they're calculating how much interest they're going to charge you, they can just say, look, we're just going to charge you 25%, we're going to charge that one time per year. Or they can do it monthly, where they charge it 12 times a year, or they can do it daily or weekly. And even though it sounds like it would be terrible if they did it daily or weekly, monthly, it all turns out to be within the same couple of dollars, all right? But we need it for the formula. We need to know what the bank is using here. Are they compounding it monthly, weekly, daily? And then finally is A. I haven't talked about what A is. A is the amount that's in there. Okay, so A is the amount in or owed, whatever it is. So it's the amount that's in the account or the amount that's owed after T years. So it's basically telling you like how much you owe, okay? It's the final calculation. All of this will give you, okay, that's how much you're going to owe. All right, that's simple interest formula. Now this one is also simple interest, but there's something slightly different here. Do we still have P, starting amount? Yes. Do we still have an interest rate? Yes. Do we still have time? Yes. Do we still have an amount at the end? What do we not have in this formula? The number of times it's compounded a year, right? That is not in this formula. There isn't not an N over here, right? So without getting too technical, this formula right here turns into that formula if you let N become infinite. And this is a calculus thing, so we don't have to get into it here. But imagine that the number of times you compounded, they're not compounding it monthly or weekly or daily or every minute or every second. They're doing it all the time. It's called continuous compounding. Then that formula somehow morphs into that. And so for this, we're going to say that we use this formula, only use it if interest is compounded continuously. That's the word I'm going to use. So when I'm giving you a problem, if you look at your review, look at the review. See number 7? It says you invest $5,300 into a 3-year CD at an interest rate of 1.32%. Assuming simple interest, find the value of the CD. Do y'all know what a CD is? Certificate of deposit?
Oh.
Yeah, not a compact disc. Certificate of deposit at a bank.